What if we could defy the ultimate speed limit of the universe? Could faster-than-light travel ever become reality? For centuries, humans have dreamed of breaking the cosmic barrier, reaching distant stars in the blink of an eye, and bending the laws of physics to our will. The idea of traveling beyond the speed of light has been a cornerstone of science fiction, but could it ever transition from fantasy to reality? The speed of light, approximately 299,792,458 meters per second, is widely considered the unbreakable limit of our universe. According to Einstein's theory of relativity, nothing with mass can ever exceed this threshold. As objects approach light speed, their mass increases, requiring an infinite amount of energy to push them beyond it. This principle has shaped our understanding of the cosmos and remains a defining constraint in physics. But what if there were a loophole? What if space itself could be manipulated to bypass this restriction? The stakes of faster-than-light travel are monumental. If humanity could overcome this barrier, interstellar travel would no longer take thousands or even millions of years. Entire galaxies would become accessible within a human lifetime. It could mean the ability to colonize exoplanets, send probes across vast cosmic distances, and perhaps even discover other intelligent civilizations. The implications stretch far beyond simple space exploration. It would rewrite the laws of physics as we know them, forcing scientists to reconsider fundamental principles that have governed the universe for over a century. The possibility of breaking the speed of light comes with more than just excitement, it carries deep controversy. Some physicists believe faster-than-light travel is entirely impossible, while others argue that theoretical loopholes could one day allow it. The debate is fueled by emerging concepts like warp drives, wormholes, and quantum mechanics. Could science uncover a way to manipulate spacetime itself? As we dive into this exploration, we'll examine the hard science behind light speed, the challenges of modern space travel, and the cutting-edge theories that suggest FTL travel could one day be achievable. We'll explore the controversy, the paradoxes, and the mind-bending implications of moving faster than light. If we can defy nature's ultimate speed limit, the universe itself may no longer be out of reach. The science of light speed. What is the speed of light? In the vast expanse of the universe, light is the fastest thing in existence. Moving at a staggering 299,792,458 meters per second, or roughly 670 million miles per hour, light defines the ultimate speed limit in physics. When you turn on a flashlight, the beam reaches across a room almost instantaneously, but in cosmic terms, even light takes time. It takes just over 8 minutes for sunlight to reach Earth and more than 4 years for light to travel from the nearest star system, Alpha Centauri. In space, distances are so immense that astronomers measure them in light years. The distance light travels in a single year, which is approximately 5.88 trillion miles. Even with our most advanced spacecraft, covering such distances would take thousands of years. This limitation has frustrated scientists and space enthusiasts alike. Could there ever be a way to travel faster? To answer this, we need to understand why light speed is considered an absolute limit and what happens when objects try to reach it. Einstein's theory of relativity and the light-speed barrier. Albert Einstein's theory of relativity, formulated in the early 20th century, revolutionized our understanding of space, time, and motion. One of its most critical revelations is that the speed of light is not just fast, it's constant in all frames of reference. No matter how fast you're moving, light will always appear to travel at the same speed relative to you. This principle leads to profound consequences. Einstein's famous equation E equals mc squared establishes a fundamental connection between energy and mass. As an object accelerates, it gains energy, which in turn increases its relativistic mass. The closer an object gets to the speed of light, the more energy it requires to continue accelerating. Theoretically, at 100% light speed, the object's mass would become infinite, meaning an infinite amount of energy would be needed to push it further. Since infinite energy is impossible to generate, Einstein's equations effectively forbid anything with mass from exceeding the speed of light. What happens as objects approach light speed? The idea of reaching or exceeding light speed is complicated by three key relativistic effects: time dilation, length contraction, and mass increase. As an object moves closer to the speed of light, time slows down relative to an outside observer. This is called time dilation. A spacecraft traveling at 90% of light speed would experience time passing much slower than it does on Earth. If an astronaut traveled near light speed for what felt like a few years, they could return to find that centuries had passed on Earth. This effect is not just theoretical. Real-world experiments have confirmed that time dilation happens. Another consequence is length contraction. From the perspective of an outside observer, an object traveling near light speed would appear to shrink along its direction of motion. This phenomenon, also known as Lorentz contraction, suggests that the faster you go, the shorter your spacecraft would appear to external observers. However, for someone inside the ship, everything would feel normal. Then there's the problem of mass increase. According to special relativity, as an object speeds up, its relativistic mass grows. This means that pushing it further requires exponentially more energy. Near light speed, this energy demand becomes extreme, making it effectively impossible to accelerate any further. Even the Large Hadron Collider, one of the most advanced accelerators on Earth, struggles to push subatomic particles to speeds approaching 99.999% of light speed. The cosmic speed limit, why physics forbids anything from exceeding it. In simple terms, the speed of light acts as a hard boundary that cannot be crossed by anything with mass. This speed limit is baked into the structure of spacetime itself. Einstein's equations tell us that exceeding light speed would result in bizarre consequences, including violations of causality, meaning events could occur before their causes, leading to paradoxes. Imagine a spaceship somehow exceeding the speed of light. If this were possible, an observer on Earth might see the spaceship arrive before it even left. This violates our fundamental understanding of time and causality. Many physicists argue that nature does not allow such paradoxes, reinforcing the idea that faster than light travel is impossible. Real-world experiments that prove relativity's effect. Though faster than light travel remains beyond our reach, relativity has been extensively tested and confirmed in experiments. One of the most famous tests involves atomic clocks on airplanes. Scientists placed highly precise atomic clocks on jets and flew them around the world. When compared to identical clocks left on the ground, the airborne clocks were found to have ticked more slowly, just as relativity predicted. Particle accelerators also demonstrate relativity's effects. When subatomic particles like muons are accelerated to near light speed, their decay rates slow down significantly, proving that time dilation is real. If we didn't account for relativity, GPS satellites would also fail, as their onboard clocks run slightly differently due to both their speed and their position in Earth's gravitational field. Despite the overwhelming evidence supporting relativity, the question remains, could there be a way around this speed limit? Could new physics, undiscovered principles, or exotic technologies allow us to break the cosmic barrier? Some scientists believe that loopholes might exist. Others argue that faster-than-light travel is fundamentally impossible. The debate continues, and as we explore the theoretical possibilities, we will step into the realm of warp drives, wormholes, and the mysteries of quantum mechanics. Current space travel limitations. How fast can we currently travel? Space travel has come a long way since the first human-made object was launched into orbit. However, compared to the vastness of the universe, our fastest spacecraft are still crawling at a pace that is nowhere near light speed. The fastest spacecraft ever built, NASA's Parker Solar Probe, reached a record-breaking 430,000 miles per hour as it slingshotted around the Sun. That's an astonishing speed by human standards, yet it would still take over 17,000 years to reach the nearest star system, Proxima Centauri. Voyager 1, launched in 1977, is another example of our slow interstellar progress. Currently traveling at around 38,000 miles per hour, it has taken over 46 years to leave the solar system. If it were headed to Proxima Centauri, it would need over 73,000 years to get there. Even SpaceX's Starship, the most advanced reusable rocket system being developed today, will still only reach a fraction of 1% of light speed. The problems with chemical rockets. Modern spaceflight relies primarily on chemical propulsion, a technology that has remained fundamentally unchanged since the dawn of the space age. Rockets burn vast amounts of fuel to generate thrust, but this method is highly inefficient for interstellar travel. The main problem is the tyranny of the rocket equation, which dictates that as a spacecraft carries more fuel to accelerate, it also increases in mass, requiring even more fuel to maintain acceleration. This exponential requirement makes conventional rockets unsuitable for deep space missions beyond our solar system. Chemical rockets also suffer from energy limitations. The energy content of rocket fuel is far too low to propel a spacecraft anywhere near light speed. The fastest human-made objects, like the Parker Solar Probe, only reach extreme speeds by using gravitational assists from planets or the Sun. Without these assists, even the most powerful rockets would struggle to exceed a few tens of thousands of miles per hour. Another issue is fuel constraints. Carrying enough fuel for a long-term deep space mission is impossible with current technology. A mission to another star would require a fuel-to-payload ratio that is completely unfeasible. Even a small spacecraft would need an astronomical amount of fuel, making chemical propulsion a dead end for interstellar travel. Even with nuclear propulsion, we're still far below light speed. Scientists have explored alternative propulsion systems to push the limits of space travel. One of the most promising ideas is nuclear propulsion, which could significantly improve speed and efficiency compared to chemical rockets. There are two primary approaches: nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP. Nuclear thermal propulsion uses heat from a nuclear reactor to expel propellant, achieving higher efficiency than chemical rockets. This could potentially double or triple the speeds of current spacecraft. However, even this advancement would still be far below the necessary speeds for interstellar travel. Nuclear electric propulsion, on the other hand, converts nuclear energy into electricity to power ion thrusters. This method is extremely efficient for long-duration missions but produces very little thrust. The slow acceleration means that even with nuclear electric propulsion, reaching another star system would take thousands of years. Scientists have also proposed nuclear fusion or antimatter propulsion, which theoretically could push spacecraft to a significant fraction of light speed. Fusion energy is incredibly powerful, and antimatter reactions release enormous amounts of energy. However, both concepts remain far from practical implementation. Controlling a sustained nuclear fusion reaction in a spacecraft is beyond our current technological abilities, and antimatter is incredibly difficult to produce and store. The vast distances to other star systems. Even if we could develop engines that travel much faster than today's rockets, the distances between stars present an overwhelming challenge. The nearest known exoplanet, Proxima b, orbits Proxima Centauri, which is 4.24 light-years away. With today's fastest spacecraft, it would take over 6,300 years to reach it. To put this into perspective, if a spacecraft somehow traveled at 10% of light speed, which is still far beyond our current capabilities, it would still take over 42 years to reach Proxima Centauri. At 50% of light speed, the journey would still take more than 8 years. For human explorers, these time frames are completely impractical unless revolutionary advancements in space travel are made. The problem becomes even more extreme when considering more distant destinations. The center of our galaxy, the Milky Way, is about 27,000 light-years away. A spacecraft moving at 1% of light speed would take 2.7 million years to get there. Even the closest galaxies, like Andromeda, are so far away that reaching them at sublight speeds is virtually impossible. The sheer scale of interstellar distances underscores why faster-than-light travel is such an enticing concept. Without it, humanity may be confined to our own solar system indefinitely. As frustrating as the limits of current propulsion may be, scientists continue to explore theoretical physics, exotic propulsion systems, and entirely new approaches that could one day allow us to break free from the constraints of conventional space travel. As we move forward, we will explore the theoretical possibilities of faster-than-light travel, including ideas like warp drives, wormholes, and quantum mechanics, which might provide a way to bypass the seemingly insurmountable speed limit of light. Could there be a way around the laws of physics as we understand them? Some scientists believe there might be. Hypothetical faster-than-light theory. The limitations of conventional space travel have forced scientists to explore radical ideas that defy our current understanding of physics. While Einstein's theory of relativity sets the speed of light as an unbreakable barrier, some theoretical models suggest possible ways around it. These ideas include bending spacetime itself, using cosmic shortcuts, or exploiting quantum mechanics to sidestep the restrictions imposed by relativity. Concepts like warp drives, wormholes, tachyons, and quantum entanglement have emerged as possible, albeit highly speculative, pathways to faster-than-light travel. Warp drives, bending space instead of moving through it. One of the most famous ideas for breaking the light-speed barrier is the Alcubierre warp drive, proposed in 1994 by physicist Miguel Alcubierre. Unlike traditional propulsion methods, which push an object forward, the Alcubierre drive suggests a way to warp spacetime itself. Instead of moving through space, a spacecraft could remain stationary within a warp bubble, while spacetime contracts in front of it and expands behind it. In theory, this would allow a ship to travel faster than light without violating Einstein's laws because the ship itself wouldn't be moving faster than light, it would be carried along by spacetime. NASA has explored this concept through the work of Dr. Harold White, who suggested that a carefully shaped warp bubble might require far less energy than initially thought. His findings hinted at the possibility of a practical warp drive, though the required energy is still astronomically high. The biggest challenge remains the staggering energy requirements. Original calculations suggested that creating a warp bubble would require more energy than the mass of Jupiter converted into pure energy. Later refinements reduced the energy requirements, but even optimistic estimates still require energy levels beyond anything currently achievable. A major challenge is the need for negative energy or exotic matter, which has never been observed in quantities sufficient to power a warp drive. Negative energy is necessary to stabilize the warp bubble, and while quantum physics allows for tiny amounts in specific conditions, generating enough to sustain a warp bubble remains purely theoretical. Even if a working warp drive could be built, there are still unresolved issues such as how to steer the bubble and avoid colliding with particles that could cause catastrophic damage upon arrival. Wormholes, cosmic shortcuts through space-time. Another potential method of faster-than-light travel involves wormholes, also known as Einstein-Rosen bridges. First proposed in the 1930s by Einstein and physicist Nathan Rosen, wormholes are hypothetical tunnels connecting two distant points in spacetime. If a spacecraft could enter one end of a wormhole and emerge at the other instantly, it would effectively bypass the need to travel through normal space, allowing for near-instantaneous interstellar travel. Physicist Kip Thorne advanced the theoretical understanding of wormholes, showing that while they might be possible under general relativity, they would require exotic matter to keep them open. Without exotic matter, a wormhole would collapse too quickly for anything to pass through. Exotic matter, with negative energy density, would counteract gravitational collapse and stabilize the wormhole's throat. However, no known process can generate or sustain such exotic matter on a scale large enough for human travel. Even if a stable wormhole could exist, other significant problems arise. One issue is stability. Quantum fluctuations could cause a wormhole to collapse unpredictably. Another is paradoxes. A traversable wormhole could allow for violations of causality, meaning that information or objects might travel back in time, potentially leading to logical contradictions. Some physicists suggest that natural wormholes might exist in the chaotic quantum foam of the universe at microscopic scales, but whether they could ever be expanded to macroscopic sizes remains unknown. Tachyons, the hypothetical faster-than-light particles. Tachyons are a class of hypothetical particles that have been proposed as a way to bypass the light-speed barrier. Unlike normal particles, which require infinite energy to reach the speed of light, tachyons are theorized to always move faster than light and could never slow down to sublight speeds. The concept of tachyons arises from certain solutions to Einstein's equations, where the mass of a particle is treated as an imaginary number. If such particles existed, they would travel backward in time from the perspective of an external observer, leading to violations of causality. This means that an event could be observed before it actually happens, raising deep philosophical and physical paradoxes. No experimental evidence has ever been found to support the existence of tachyons. High-energy physics experiments, including those conducted at the Large Hadron Collider, have searched for signs of tachyon-like behavior, but nothing conclusive has emerged. Many physicists believe that tachyons, if they exist, would be confined to theoretical models rather than real-world physics. Even if tachyons were real, utilizing them for practical faster-than-light travel would be another challenge entirely. Their supposed properties suggest they would be highly unstable, difficult to detect, and likely impossible to control. As intriguing as tachyons are, they remain in the realm of speculation with no clear path. Quantum tunneling and entanglement, loopholes in physics. Quantum mechanics, the branch of physics governing the behavior of particles at the smallest scales, has introduced concepts that appear to challenge relativity's speed limit. One such phenomenon is quantum tunneling, where particles can pass through energy barriers that classical physics says should be impenetrable. Experiments have shown that tunneling sometimes happens at speeds that seem to exceed the speed of light. However, this effect does not transmit useful information faster than light, so it cannot be used for travel or communication. Another quantum phenomenon often linked to faster-than-light speculation is quantum entanglement. When two particles become entangled, their states remain correlated no matter how far apart they are. If one particle is measured, the other reacts instantly, even if separated by vast distances. Albert Einstein famously called this effect spooky action at a distance. Despite how it appears, quantum entanglement does not allow for faster-than-light communication or travel. No actual information is transmitted between entangled particles, meaning that while the effect is instantaneous, it does not violate relativity in a way that could be exploited for FTL travel. The deeper implications of entanglement are still being explored, but at present, it offers no clear path to breaking the light-speed barrier. While these quantum effects suggest that nature is far more complex than classical physics predicts, they do not yet provide a roadmap for faster-than-light travel. Scientists continue to investigate whether undiscovered principles in quantum mechanics could someday be harnessed to challenge the cosmic speed limit. Are we any closer to faster-than-light travel? Despite these fascinating theories, there is currently no experimental proof that faster-than-light travel is possible. Warp drives require unattainable energy levels, wormholes are purely hypothetical, tachyons remain undiscovered, and quantum effects, while bizarre, do not allow for FTL motion. Every known method for exceeding light speed runs into insurmountable physical and theoretical obstacles. Yet, history has shown that science often advances in ways no one can predict. Just as quantum mechanics and relativity overturned 19th-century physics, new discoveries may one day challenge what we currently believe about spacetime and motion. If faster-than-light travel is ever to become reality, it will likely require a complete shift in our understanding of physics, possibly involving forces, dimensions, or energy sources that we have yet to comprehend. The pursuit of interstellar travel continues, driven by human curiosity and the desire to reach beyond the limits of our own solar system. While today's science suggests that the speed of light is an unbreakable barrier, the search for loopholes, unknown laws, or new dimensions of physics remains ongoing. If the past century of discovery has taught us anything, it's that the universe is full of surprises, and the impossible might one day become possible. The controversy and paradoxes of faster-than-light travel, if ever proven possible, would revolutionize physics and redefine humanity's understanding of space, time, and causality. However, the very idea of exceeding the speed of light brings profound consequences, leading to paradoxes that challenge the foundations of logic and scientific reasoning. The laws of physics, as we understand them, are built upon the fundamental principle of causality, cause and effect occurring in a consistent order. Faster-than-light travel introduces scenarios where this natural order could be disrupted, leading to paradoxes that suggest FTL movement might be not just impractical, but outright impossible. The causality paradox: can FTL travel send information back in time? Causality is the principle that an effect cannot occur before its cause. This fundamental rule governs everything from the motion of objects to the flow of time itself. If faster-than-light travel were possible, it could lead to violations of causality, meaning that events could happen before their causes. In theoretical physics, this is known as the causality paradox, and it presents one of the biggest roadblocks to FTL travel. Imagine a spaceship that can exceed the speed of light. If an astronaut sends a message while moving at FTL speeds, observers on Earth might detect the message before it was even sent. This would mean that information could travel backward in time, violating the principle of cause and effect. In some cases, this could allow people to receive warnings about future events before they happen, creating logical contradictions where an event is prevented before it ever takes place. This paradox is deeply problematic because it implies a breakdown of reality as we understand it. If causality no longer holds, then logical consistency itself is threatened. Could FTL travel be possible if physics allows for time loops and contradictions? Some physicists argue that certain unknown principles might prevent causality violations, while others suggest that FTL is fundamentally impossible because it leads to these logical paradoxes. The twin paradox: would faster-than-light travelers age differently? The twin paradox is a well-known thought experiment in Einstein's theory of relativity, demonstrating how time dilation affects travelers moving at high speeds. If one twin remains on Earth while the other embarks on a journey near the speed of light, time for the traveling twin slows down relative to the twin who stays behind. Upon returning, the traveling twin would have aged significantly less than their Earthbound sibling. Now, imagine this same scenario with faster-than-light travel. If a person were to travel beyond the speed of light and return to Earth, would they experience extreme aging effects? The situation becomes even stranger when considering relativity's implications for FTL movement. Some models suggest that an FTL traveler could appear younger than when they departed, essentially experiencing reverse aging in the eyes of an outside observer. This raises fundamental questions about the nature of time and motion. If an object moving at near light speeds already experiences significant time dilation, an object moving beyond light speed could, in theory, move backward in time from another observer's perspective. This presents another paradox. If an astronaut were to leave on an FTL voyage, they might arrive at their destination before they had even departed. The logical implications of this are staggering and remain one of the biggest reasons why physicists argue that breaking the light speed barrier would require entirely new laws of physics. The grandfather paradox. Could FTL travel enable time travel? The grandfather paradox is one of the most famous time travel paradoxes, often used as an argument against the possibility of moving backward in time. The paradox is simple. If time travel were possible, a person could hypothetically travel to the past and prevent their own grandfather from meeting their grandmother. This action would prevent the person from ever being born, leading to a contradiction. If they were never born, then they couldn't have traveled back in time in the first place. Now, consider how faster-than-light travel might create a similar issue. If FTL motion allows for causality violations, then a spaceship could theoretically move faster than light, turn around, and arrive back in time before its departure. This would allow someone to alter past events, leading to scenarios where an effect occurs without a clear cause. One possible resolution to the grandfather paradox comes from the idea of self-consistency. Some physicists propose that the universe might prevent time travel paradoxes by ensuring that any changes made in the past must be consistent with the present. In other words, no traveler could alter history in a way that contradicts their own existence. However, this idea remains purely speculative, and there is no experimental evidence to support or refute it. If FTL travel inherently leads to time travel paradoxes, then one of two conclusions must be drawn. Either time travel is somehow prevented by an unknown physical mechanism, or FTL travel itself is impossible. This fundamental uncertainty continues to fuel the debate about whether superluminal speeds can ever be reached. Opposing views from physicists: is faster-than-light travel impossible? While mainstream physics upholds the light speed limit as an absolute barrier, there are divided opinions on whether FTL travel is fundamentally impossible or simply beyond our current understanding. Some physicists argue that the known laws of physics strictly prohibit any object with mass from reaching or exceeding the speed of light. The arguments against FTL are primarily based on relativity, which shows that infinite energy would be required to push an object past this barrier. The presence of causality violations, paradoxes, and potential time loops further supports the idea that nature simply does not allow anything to exceed light speed. On the other hand, some theoretical physicists believe that workarounds might exist. Ideas such as wormholes, warp drives, and negative energy fields suggest that the universe might permit certain exceptions to the light speed limit under very specific conditions. Theoretical models have proposed ways to manipulate spacetime itself to allow for apparent FTL travel without directly breaking relativity. These models remain speculative, but they offer tantalizing hints that new physics could one day provide unexpected solutions. Some physicists also argue that future discoveries in quantum gravity, extra dimensions, or dark energy might redefine our understanding of spacetime and motion. If unknown forces or particles exist that interact differently with spacetime than currently understood, then FTL travel may not be as impossible as relativity suggests. While no concrete evidence supports these ideas yet, ongoing research continues to probe the fundamental nature of the universe. The philosophical debate: does FTL travel violate the laws of nature? Beyond the scientific arguments, faster-than-light travel also raises deep philosophical questions. If the universe strictly enforces the light speed limit, then this might imply that the fundamental laws of physics are fixed and immutable. This would suggest that humanity is permanently confined to its local cosmic neighborhood, with interstellar travel limited to sublight speeds. However, if FTL travel is possible under certain conditions, this would mean that the universe is far stranger than we currently understand. It would suggest that spacetime itself can be manipulated in ways that defy our current knowledge. The implications extend beyond travel itself. Faster-than-light motion could mean that time is more fluid than we assume, or that alternate timelines and parallel realities exist. If the laws of physics allow for paradoxes and causality violations, then the nature of reality itself might be more flexible than previously believed. Some philosophers argue that time might not be an absolute sequence of events but rather a construct of human perception. If this is true, then perhaps FTL travel could reveal deeper truths about the structure of the cosmos. Despite all the theories, paradoxes, and debates, one thing remains clear: faster-than-light travel challenges the very fabric of our understanding of reality. Whether it is forever impossible or merely awaiting a breakthrough remains one of the greatest scientific mysteries of our time. The debate continues, with scientists and theorists exploring every possibility, from spacetime manipulation to exotic physics, in the quest to determine whether the universe holds a secret pathway beyond the speed of light. Cutting-edge scientific experiment. CERN's faster-than-light neutrino experiment. Did scientists break the speed of light? In 2011, the scientific community was rocked by a shocking announcement from the OPERA experiment at CERN. Researchers working at the Gran Sasso laboratory in Italy reported that they had measured neutrinos traveling faster than the speed of light. The results suggested that these subatomic particles had arrived 60 nanoseconds earlier than expected, potentially overturning one of the most fundamental laws of physics. If true, Einstein's theory of relativity, establishing the speed of light as the ultimate limit, could be wrong, opening the door to entirely new understandings of space, time, and motion. The implications were staggering. If neutrinos could exceed light speed, then causality violations and time travel paradoxes might no longer be theoretical, they could be real. Physicists around the world scrambled to analyze the results. Some speculated that new physics was at play, while others remained skeptical, knowing that extraordinary claims require extraordinary evidence. Months of rigorous scrutiny followed, and eventually, the mystery was solved. The faster-than-light neutrinos had not, in fact, broken Einstein's speed limit. Instead, the discrepancy was traced to a faulty optical fiber cable in the timing system. The data had been affected by an unexpected delay, leading to a miscalculation in the neutrino's arrival time. Once the error was corrected, neutrinos were found to behave exactly as predicted, always traveling at speeds below or at the speed of light, never beyond it. Although the results were ultimately disproven, the event demonstrated how even the most well-established scientific principles must always be tested. The search for faster-than-light phenomena continues, but the opera incident reinforced the importance of precision in experimental physics. NASA's Breakthrough Propulsion Physics program, what have they found? NASA has long been at the forefront of space exploration, and in recent years, it has also explored exotic propulsion concepts that challenge conventional physics. One of the most intriguing initiatives is NASA's Breakthrough Propulsion Physics (BPP) program, an effort dedicated to researching advanced propulsion technologies that could one day enable faster-than-light travel. One of the key areas of study in this program has been the idea of warp fields, inspired by the Alcubierre warp drive. In 2012, Dr. Harold White, a physicist at NASA's EagleWorks laboratories, proposed a modified version of the Alcubierre metric that might reduce the enormous energy demands previously calculated for warp travel. His work suggested that a carefully shaped warp bubble could be created with far less energy than originally thought. To test this concept, White and his team conducted small-scale experiments to detect tiny fluctuations in spacetime, attempting to generate the first observable evidence of a warp effect. Although no definitive breakthroughs have been achieved yet, the research remains ongoing. If scientists can find a way to manipulate spacetime at will, it could represent a monumental leap forward in our ability to traverse the cosmos. Another avenue of research within NASA's propulsion studies is quantum vacuum fluctuations, which involve tapping into the energy of empty space itself. Theoretical models suggest that the vacuum of space is not truly empty, but rather a sea of constantly shifting energy fields. If a spacecraft could harness this energy, it might be able to create a propulsion system that bypasses conventional speed limits. Despite these promising areas of study, no experimental evidence has yet confirmed the feasibility of faster-than-light travel. However, the fact that NASA is investing in such research suggests that the dream of breaking the light-speed barrier is not entirely out of reach. Current research into negative energy and warp fields, is there hope? One of the most significant challenges for faster-than-light travel is the requirement for negative energy, a bizarre and exotic form of energy that behaves opposite to normal matter. Negative energy is necessary for concepts like wormholes and warp drives. as it counteracts gravitational forces that would otherwise cause these structures to collapse. While negative energy might sound like science fiction, quantum mechanics suggests that it does exist, at least in tiny amounts. The Casimir effect, a phenomenon observed in quantum field experiments, has demonstrated that two closely placed conductive plates can generate a measurable force due to quantum fluctuations in the vacuum. This effect is one of the few pieces of experimental evidence suggesting that negative energy is real, but whether it can be harnessed in meaningful amounts remains an open question. Several theoretical physicists, including Kip Thorne and Matt Visser, have explored how negative energy could be used to stabilize wormholes or create Alcubierre-style warp bubbles. The biggest problem is that the amount of negative energy required for such feats is currently far beyond what can be generated. Some estimates suggest that stabilizing a traversable wormhole would require more energy than is contained in an entire galaxy. Despite these challenges, some scientists remain hopeful. Theoretical models have suggested that exotic materials, potentially linked to dark energy, could provide the necessary negative energy densities. If researchers can find a way to generate and control negative energy, it would represent a monumental breakthrough for both physics and space travel. One particularly fascinating area of study involves metamaterials, specially engineered materials that can manipulate light and energy in unusual ways. Some experiments have shown that certain metamaterials can create negative refraction, bending light in ways that seem impossible under normal conditions. While this research is still in its infancy, it raises the tantalizing possibility that future technologies might be able to engineer spacetime itself to allow for superluminal travel. Breakthrough Starshot, a practical approach to interstellar travel. While many FTL concepts remain purely theoretical, one initiative is actively developing a practical approach to interstellar travel. Breakthrough Starshot, a project funded by billionaire Yuri Milner and supported by physicists like Stephen Hawking before his passing, aims to send small, light-propelled spacecraft to the nearest star system, Proxima Centauri, within a human lifetime. Instead of using conventional rockets, Breakthrough Starshot proposes using laser propulsion to accelerate tiny, gram-sized spacecraft to speeds approaching 20% of the speed of light. This would be achieved by firing an array of high-powered lasers from Earth, pushing a fleet of miniature spacecraft equipped with ultra-thin, light sails. If successful, these spacecraft could reach Proxima Centauri in just over 20 years, a timeframe far shorter than conventional chemical propulsion could ever achieve. This project represents a significant step forward in realistic interstellar travel. While it is not truly faster than light, it demonstrates that new propulsion methods can dramatically reduce travel times to other star systems. If successful, it could pave the way for larger, crewed missions in the future, potentially using advanced propulsion systems like fusion drives or antimatter rockets. One of the biggest challenges for Breakthrough Starshot is developing a laser system powerful enough to push the spacecraft to such high speeds. Current laser technology is not yet capable of delivering the required levels of energy efficiently. There is also the challenge of interstellar dust. Tiny particles traveling at relativistic speeds could pose a significant risk to the miniaturized probes. Despite these hurdles, Breakthrough Starshot represents humanity's most serious attempt yet at sending a probe beyond our solar system. While it does not break the light-speed barrier, it suggests that innovative propulsion methods could allow us to explore nearby stars within a human lifetime. If this technology is further refined, it could one day be adapted for larger spacecraft, eventually bringing us closer to achieving the dream of interstellar travel. Are we on the verge of a breakthrough? The search for faster-than-light travel continues, with experimental research pushing the boundaries of physics. While no definitive evidence has emerged to suggest that FTL travel is possible, every new discovery brings us closer to understanding the fundamental limits of the universe. Advances in quantum mechanics, negative energy, and metamaterials could hold the key to unlocking new propulsion technologies that defy our current understanding of motion and speed. With initiatives like NASA's propulsion studies and Breakthrough Starshot, humanity is actively working toward interstellar travel, even if it remains at sublight speeds for now. The dream of reaching the stars has never been stronger, and while the speed of light remains unbroken, the pursuit of new physics continues. If there is a way to surpass this cosmic barrier, it may come from a discovery yet to be made, one that challenges everything we know about space, time, and the very nature of reality itself. Could aliens have achieved faster-than-light travel? The question of whether extraterrestrial civilizations have cracked the secret to faster-than-light travel is one of the most debated topics in both scientific and speculative communities. If advanced alien species exist, have they already achieved what humans can only dream of? Have they mastered propulsion systems that bypass the limitations of physics as we currently understand them? Reports of UFO sightings, ancient astronaut theories, and the sheer mathematical probability of advanced civilizations suggest that if FTL travel is possible, it may have already been achieved by beings far more technologically advanced than us. Are UFO sightings evidence of faster-than-light propulsion? Unidentified flying objects, or UFOs, have been reported for decades, often exhibiting movements that defy conventional physics. Military pilots, commercial airline crews, and civilians have described objects accelerating at incredible speeds, making sharp turns that should be impossible under known laws of aerodynamics, and even vanishing instantly. Some of these sightings have been dismissed as misidentified natural phenomena, secret military technology, or optical illusions, but others remain unexplained. One of the most famous cases that fueled speculation about advanced alien technology is the Pentagon's declassified UFO reports, which acknowledged sightings of unidentified aerial phenomena, UAP, that displayed no visible means of propulsion and movements beyond known human capabilities. Pilots reported objects that could accelerate from a standstill to hypersonic speeds in an instant, without producing heat signatures, exhaust plumes, or sonic booms. These characteristics would suggest a propulsion system fundamentally different from anything human engineering has developed. If these objects are indeed controlled by an intelligent extraterrestrial race, it raises a compelling question. Have they achieved faster-than-light travel or some form of exotic propulsion that manipulates space-time? While mainstream science remains cautious about drawing conclusions, some physicists have speculated that these UAPs might not be moving through space conventionally at all. Instead, they could be bending spacetime around them, much like theoretical warp drives suggest. This would allow them to travel vast distances almost instantaneously, bypassing the speed limits imposed by relativity. Skeptics argue that until definitive proof is provided, attributing UFO sightings to FTL-capable aliens remains speculative at best. However, the possibility remains open that if an advanced civilization has mastered physics beyond human understanding, the strange objects observed in our skies could be a glimpse into what lies ahead for us in the distant future. Ancient astronaut theories. Did extraterrestrials use FTL to visit Earth? The idea that extraterrestrial beings may have visited Earth in the distant past is a theory that has persisted for decades. Proponents of the ancient astronaut theory argue that certain archaeological discoveries, myths, and unexplained structures suggest the presence of advanced visitors who may have possessed technology far beyond human capabilities at the time. If an alien civilization had developed faster than light travel thousands or even millions of years ago, could they have journeyed to Earth, influencing ancient cultures and leaving behind clues? Some researchers point to the Great Pyramids of Giza, the Nazca Lines in Peru, and the megalithic structures of Puma Punku as potential evidence of extraterrestrial intervention. These structures exhibit levels of precision, astronomical alignment, and construction techniques that some believe were impossible with the primitive tools available to ancient civilizations. While mainstream archaeologists credit these achievements to human ingenuity, ancient astronaut theorists suggest that if aliens possessed FTL travel, they could have made periodic visits to Earth, sharing knowledge and technology. Ancient myths and texts from civilizations like the Sumerians, Mayans, and Hindus also describe beings that arrived from the sky, often in chariots of fire or flying machines. The Mahabharata, an ancient Indian epic, speaks of flying crafts known as vimanas, which allegedly possessed advanced propulsion systems capable of traveling vast distances. While skeptics dismiss these stories as mythological exaggerations, others argue that they could be records of real encounters with extraterrestrial visitors. If an alien race achieved interstellar travel long before humans, their knowledge of physics would likely surpass ours by an unimaginable degree. They might have discovered ways to fold space, traverse wormholes, or use unknown forms of energy to defy our concept of light speed. However, without physical evidence, the ancient astronaut theory remains an intriguing but unproven idea. If an advanced civilization cracked FTL, how would they explore the galaxy? The universe is vast beyond comprehension, with billions of stars in each galaxy and billions of galaxies in the observable universe. If an extraterrestrial species managed to develop faster than light travel, how would they go about exploring such an immense cosmic landscape? Given the challenges of interstellar distances, even a Type 1 or Type 2 civilization on the Kardashev scale, which measures a civilization's ability to harness energy, would require advanced propulsion far beyond chemical rockets or even nuclear propulsion. A civilization capable of FTL travel would likely structure its exploration efforts based on efficiency, sustainability, and the ability to monitor multiple star systems simultaneously. They could establish outposts or relay stations in strategic locations across the galaxy, using them as launching points for further exploration. If their technology allowed them to travel vast distances in a matter of minutes or hours, they might even operate in a way similar to human airline routes, creating interstellar trade networks or communication hubs. Another possibility is that FTL-capable civilizations might employ autonomous AI-driven probes, seeding their technology across different parts of the galaxy while remaining at a distance themselves. These probes could be self-replicating, using local materials to build new versions of themselves, slowly expanding their presence without requiring large crews of biological beings. This idea aligns with the concept of von Neumann probes, hypothetical self-replicating machines designed to explore the cosmos efficiently. If a species had mastered warp drives, wormholes, or space manipulation, they could bypass the need for conventional travel altogether. Instead of physically moving from point A to point B, they might bend spacetime, allowing their ships to jump across vast cosmic distances instantaneously. This method would be the ultimate solution to the challenges of interstellar exploration, as it would eliminate time constraints and relativistic effects altogether. An even more advanced civilization might not even need physical ships in the way we imagine them. Some theories suggest that post-biological civilizations, civilizations that have uploaded their consciousness into artificial systems, might exist as energy-based entities capable of moving through the universe in ways we cannot yet comprehend. If such beings exist, their travel methods might be so far beyond human understanding that even FTL travel could seem primitive by comparison. The question of whether extraterrestrials have already mastered faster than light travel remains unanswered. While no definitive evidence exists to confirm the presence of FTL-capable aliens, the sheer number of exoplanets, the potential for intelligent life, and the unexplained nature of some UFO phenomena suggest that the possibility cannot be ruled out. If a civilization has already found a way to surpass the light-speed barrier, it would mean that the universe is not just full of life, but potentially connected in ways we have yet to discover. Humanity is still in the early stages of understanding the universe, but as science progresses, we may one day uncover evidence that civilizations far older than ours have already achieved what we are still striving toward. Whether through warp drives, wormholes, or unknown physics, the possibility remains open that somewhere in the galaxy, intelligent beings are already traveling the stars at speeds beyond our wildest imagination. Future possibilities and theoretical breakthroughs. The pursuit of faster-than-light travel is not merely a speculative fantasy, it is an ongoing scientific challenge that could redefine humanity's place in the universe. While current physics places strict limits on how fast objects with mass can travel, emerging theories and future technological advancements may one day allow us to break through these barriers. Concepts such as harnessing dark energy, creating artificial wormholes, leveraging AI and quantum computing, and predicting the trajectory of space travel over the next century offer fascinating glimpses into what might be possible. Could dark energy be harnessed for faster-than-light travel? Dark energy is one of the greatest mysteries in modern physics. It is an invisible force that appears to be driving the accelerated expansion of the universe, yet scientists still do not fully understand what it is. Observations of distant galaxies show that space itself is stretching, meaning that regions of the universe are moving apart faster than the speed of light. Not because they are physically traveling at such speeds, but because space itself is expanding. If dark energy is responsible for this acceleration, could it be manipulated to create faster-than-light propulsion? One hypothesis suggests that if dark energy could be artificially generated or controlled, it might be possible to create a localized expansion of space around a spacecraft, mimicking the effect of the universe's expansion. This idea is similar to the Alcubierre warp drive, which proposes compressing space ahead of a ship and expanding it behind, effectively allowing faster-than-light movement without breaking the laws of physics. However, dark energy remains elusive, and there is currently no known way to harness or manipulate it. The key problem with dark energy as a propulsion source is its low energy density. While it dominates the large-scale structure of the cosmos, it is incredibly weak in any localized region. If scientists could discover a way to amplify its effects, they might unlock a completely new method of space travel. Some researchers speculate that future quantum field studies or new discoveries in cosmology may provide insights into how dark energy operates. If this force is truly responsible for the universe's rapid expansion, then understanding its properties could be a game-changer for interstellar travel. Is artificial wormhole creation realistic? Wormholes remain one of the most intriguing possibilities for FTL travel, providing theoretical shortcuts through spacetime that could connect distant points instantly. The problem is that while wormholes are mathematically possible under general relativity, they are incredibly unstable and would collapse almost instantly unless stabilized by exotic forms of negative energy. The question is whether it will ever be possible to artificially create and stabilize a traversable wormhole. In theory, a civilization with advanced control over gravity and spacetime could construct a wormhole by manipulating quantum fields or using extreme amounts of energy to bend spacetime into a loop. Some physicists believe that if negative energy could be generated in sufficient quantities, it might be possible to keep a wormhole open long enough for spacecraft to pass through. However, the energy requirements remain astronomical, and current physics offers no clear method to generate or sustain such exotic conditions. Recent studies in quantum gravity and string theory suggest that microscopic wormholes might naturally exist at the Planck scale, the smallest measurable unit of the universe. If this is the case, future advancements in particle physics and quantum mechanics might allow scientists to manipulate these structures, expanding them into usable passageways. While this remains speculative, research into quantum entanglement, black hole physics, and high-energy particle collisions could eventually lead to breakthroughs in artificially creating or stabilizing wormholes. If artificial wormholes ever become a reality, they could offer a true faster-than-light transportation system, bypassing the need to physically move through space at superluminal speeds. The ability to instantly connect distant points in spacetime would make interstellar and even intergalactic travel feasible, opening the universe to exploration in ways that are currently unimaginable. Could ion quantum computing accelerate faster than light research? Artificial intelligence and quantum computing are already transforming many areas of science, from climate modeling to drug discovery. As computational power continues to grow, AI-driven models and quantum processes could play a crucial role in simulating, testing, and uncovering new physics related to faster-than-light travel. AI is particularly useful in analyzing complex equations, optimizing energy consumption, and generating new hypotheses that human researchers might overlook. Advanced machine learning algorithms could help simulate spacetime warping, gravity distortions, and quantum fluctuations, identifying patterns that could lead to new insights into propulsion physics. AI-powered research systems might even assist in engineering exotic materials needed for future warp drives or wormhole stabilization. Quantum computing, on the other hand, offers the potential to solve calculations that classical computers would take millions of years to process. Quantum systems excel at handling probability-based problems, making them ideal for modeling quantum field interactions, understanding dark energy, and exploring new particle physics theories. If FTL travel requires harnessing exotic forces at the quantum level, then quantum computers might be the key to unlocking these unknowns. In the near future, collaborations between AI researchers, physicists, and aerospace engineers could significantly accelerate FTL research. AI-driven simulations could test thousands of theoretical propulsion models simultaneously, filtering out unviable concepts and identifying the most promising avenues for further study. By combining AI's analytical power with quantum computing's ability to model subatomic phenomena, scientists may uncover entirely new laws of physics that provide unexpected pathways to interstellar travel. What physicists predict for the next 100 years in space travel? Predicting the future of space travel is always a challenge, but based on current advancements and theoretical research, the next century could bring profound breakthroughs. While true faster-than-light travel may not be achievable within the next 100 years, significant strides in propulsion technology, energy manipulation, and space exploration could lay the foundation for interstellar travel. Within the next few decades, we are likely to see continued improvements in nuclear propulsion, laser-driven spacecraft, and advanced ion thrusters, allowing for faster travel within our solar system. The Breakthrough Starshot initiative, which aims to send ultra-fast probes to Proxima Centauri using light sail technology, could prove that interstellar travel, though slow by FTL standards, is possible with creative engineering. As AI and quantum computing evolve, physicists may begin uncovering new principles of spacetime physics, leading to unexpected propulsion discoveries. The next 50 years may bring experimental breakthroughs in controlling negative energy, detecting hidden dimensions, or generating artificial gravity fields, all of which could be stepping stones toward FTL research. By the end of the century, the most ambitious predictions involve controlled wormhole travel, artificial spacetime manipulation, and new energy sources derived from quantum fluctuations or dark energy. If major discoveries occur in fields such as string theory or quantum gravity, humanity may gain the ability to alter spacetime itself, opening the door to technologies that are currently beyond our comprehension. The ultimate breakthrough would be the ability to manipulate spacetime in real time, creating localized distortions that allow for faster-than-light travel. While this remains purely theoretical, history has repeatedly shown that scientific progress can outpace expectations. What was once thought impossible, human flight, space travel, quantum entanglement, has all become reality through relentless innovation. The next 100 years could be an era of profound discovery, with physics uncovering deeper truths about the universe and technology bringing us closer to interstellar travel. Whether or not humanity achieves faster-than-light propulsion, the quest itself will likely lead to groundbreaking advancements in energy, computing, and space exploration. If an FTL breakthrough does occur, it may not just change how we travel, it could redefine our understanding of time, reality, and our place in the cosmos. Faster-than-light travel has remained one of the greatest challenges in modern physics, a concept that excites the imagination but defies the fundamental laws of the universe as we currently understand them. The scientific barriers to breaking the cosmic speed limit are immense, with Einstein's theory of relativity setting light speed as an unbreakable boundary. The energy required to propel an object past this limit appears infinite, and the paradoxes introduced by FTL motion threaten to unravel our very understanding of cause and effect. Despite these obstacles, theoretical models offer glimpses of wild possibilities, from warp drives that bend spacetime to wormholes that act as shortcuts through the cosmos. The study of quantum mechanics continues to reveal strange and unexpected behaviors, suggesting that the universe may still hold secrets that could challenge everything we think we know about motion, time, and space. While mainstream physics argues that faster-than-light travel remains impossible, some scientists believe that with the right breakthroughs, humanity could one day find a loophole in the laws of nature. The question remains, will we ever break the cosmic speed limit? Right now, the answer is no. Every known law of physics suggests that traveling faster than light is impossible. But history has shown that scientific frontiers are constantly expanding, with discoveries that once seemed out of reach becoming reality. Just as humans once believed that heavier-than-air flight was impossible, perhaps faster-than-light travel is simply waiting for a breakthrough. If the impossible does become possible, it will change the future of humanity forever. Until then, the quest continues. Subscribe for more deep dives into the mysteries of the universe, and let's keep exploring the limits of what is known and what might one day be achieved.